Hi everyone, this is Gabriella. I'm a PhD student at the University of South Australia, and I'm going to be presenting to you my paper entitled A Conceptual Framework for Construction and Demolition Waste Prevention in Buildings Design Phase. When it comes to sustainability in the building sector, beyond the GHG emissions and energy use, waste started to gain global attention, especially since without any consideration, this type of waste can have a significant impact on both the economy and environment, and can represent almost 40% of a country's total waste. So the effects of construction and demolition waste are definitely noteworthy, and the need for a proper management strategy becomes clear. The environmental evaluation of processes related to construction and demolition waste can be analyzed through the waste hierarchy triangle, basically a tool that indicates preferable solutions to reduce and manage solid waste. As shown in the diagram, the concept of avoiding waste is preferable, since it offers preventive measures. Particularly for buildings, the best way to apply this perception is during the design phase, where there is a higher chance of optimizing project alternatives for waste efficiency. With that in mind, waste prevention needs to consider impact from a life cycle approach, so that waste streams are comprehensively analyzed and accurately dealt with during the design phase. It also calls for a focus on human factors, as its attitude, reality, context, and necessities will orientate this development. In addition to that, the amount of data and the requirement of computational integration expect the combination of technological base as well. Therefore, the combination of BIM and LCA is seen in the literature as an important step towards waste minimization during the early stages of a building, because of one's potential to store and manage essential information and share it with multiple stakeholders, and the other's holistic environmental assessment. But although currently widespread as suitable approach, the interoperability between BIM and LCA still faces many challenges from both a technical and informational view. For this reason, this paper aims to support proper decision-making regarding construction and demolition waste during the design phase of a building. A conceptual framework is proposed to introduce the LCA parameters that need refinement in order to better assess each material's waste stream and environmental impact at the early stages of a building's life cycle. To do so, a literature search on review papers discussing BIM and LCA integration has been carried out, and afterwards, a conceptual framework was introduced to address the necessary refinements needed for a construction and demolition waste management. After a comprehensive review of the papers, the overall challenges of BIM and LCA integration were better identified through different viewpoints, mainly divided in informational, modeling, technical, and organizational issues. Technical and organizational issues, although crucial for the proper integration and automation of the link between BIM and LCA, are not the focus of this paper, which targets the information management and modeling refinement. The biggest information and modeling issues are related to level of detail, environmental data, building stages, and goal and scope. Or better yet, the absence of this information in current assessments. The appropriate LOD must be taken into account, as it will define the amount and quality of data that will be provided to the lifecycle inventory. Beyond that, it can actually help the calculation of end-of-life impact, as a higher LOD gives precise information on materials that can be divided in waste typology, which is important to formulate precise waste streams. Environmental data from building materials or elements to develop an inventory are also necessary and will be provided by databases and environmental product declarations, EPDs. There are several databases currently available. The challenge is that most times the amount of information regarding environmental impact stored on them is not enough. Most regions do not even have fully refined databases, and the use of genetic runs hinders the assessment of realistic environmental impacts. Even when there is data based on a broader life cycle that calculates processes up to the end of life, it's usually based on generic information or even a generalization of common scenarios, such as landfill disposal. As a result, construction and demolition waste is not properly accounted for on the overall building impact, and is not even considered during the decision-making process at the design phase. Regarding building stages, a building LCA is divided in 4 main stages. We have the product, construction, use, and end of life. And also additional information on potential benefits and loads if necessary. Theoretically, the choice of stages will be based on the goal and scope of the analysis, but in reality, it is critically linked to the availability of information. It is clear that there is a tendency to focus on the product phase, which can be explained by the temporal facilitation of it. During the design of a building, most of the product phase already happened, so the data is available and fairly precise. After the construction phase, limitations based on scenarios and assumptions start to arrive. This means that the development of a proper cradle-to-grave BIM-based environmental assessment is still scarce. With all that said, it is interesting to see that beyond the integrational issues, there are critical matters regarding information and modeling inside the LCA that need to be addressed and are currently under study. During the design phase, if the user has access to the BIM model and LCA results, regardless of how the integration is done, the data from the lifecycle calculation needs to be accurate to properly help the decision-making process. However, there are several parameters that are commonly based on assumptions or generic data, if defined at all, since although waste is generated during different stages of a building's life cycle, only 27% of BIM-based LCA studies consider construction and demolition waste production. So a conceptual framework is proposed as a first step to guide the refinement of modeling processes and improve the materials waste streams. This framework shows the parameters required to develop a comprehensive LCA based on the sources and factors of waste during a building's life cycle. It also indicates the level of difficulty for obtaining these parameters. During the construction phase, causes of construction and demolition waste are linked to the transportation and construction or installational processes. Actions such as damaging goods during transportation, difficulties for delivering vehicles, insufficient protection during unloading, offcuts, application processes are potential drivers. Hence, a wastage percentage per building material is required to account for the necessary over-manufacturing. The use phase, specifically the stages of maintenance, repair, replacement, they require data on each building material replacement factor based on the lifespan of the studied material. Due to the long building lifespan, the end-of-life phase and the potential benefits and loads have the highest assumption rates, as well as non-accountability in papers. The deconstruction stage requires knowledge on the type of demolition in order to enable calculations on energy, water, and diesel consumptions. The transport to disposal firstly need the end-of-life scenarios of the building materials. The waste processing stage will take into account the chosen end-of-life scenario of each building material as well. Lastly, the potential benefits and loads require information beyond the system boundary, based on the end-of-life scenarios of each materials. Even though it's not mandatory, this phase gives a better representation of reality by adding the benefits of any recovery, reuse, or recycle to the calculation. The development of methods to properly combine BIM and LCA is growing, especially in terms of design flow, as well as the attempts to classify and standardize its integration. However, beyond the technical integrational issues, there are critical matters regarding information and modeling before this integration takes place. In conclusion, to properly inform the designer of the environmental impact of each material, the building's LCA needs refining. There are already some easily attainable data, such as transportation, which are still not included in the evaluation simply because they're part of the end-of-life phase. Some parameters are dependable on construction technology and user behavior, such as wastage during construction and demolition consumption. And finally, some points are defined as challenging. Building material replacement factor, for example, that nowadays is not standardized between materials and it is commonly used as generic average for all building components. Or the type of treatment and percentage of waste that is going to it, which also hinders the potential of recyclability and reusability that can be added to the assessment and are usually not included on the calculation because of the building's service life. This research is part of an ongoing project to develop a computational platform for reducing construction and demolition waste during the design phase with the use of BIM and LCA. Next steps will be the refinement of each parameter with the use of statistical estimation and uncertainty analysis, so that the LCA can deliver a more reliable environmental impact result. These are some of the references used in this research. For a complete list, you just need to access the whole paper. Thank you so much for listening.